So for our third lesson here of chapter 23, we're going to finish off this idea of the limiting process that we started in lesson 2. So let me give you kind of the quick overall idea here that we're trying to accomplish. We were given in the initial problem, we were given a function for time that you see right here. And so it's the position or this article that's being moved across a straight line over a period of time. So t represented time. This represents the overall position function that we're dealing with. And ultimately, we are looking for an instant rate of change. So we start out with the idea of the average rate of change. So we said, here's the average rate of change from 1 second to 2 seconds. Here's the average rate of change from 1 second to 1.5 seconds. But all those were average rates of change. Ultimately, and this is what we're looking for down here now at the bottom, is what if I don't want an average rate of change? What if I want an instant rate of change? So I only want to know what is the instant rate of change at 1 second. So what we did here on the last part of lesson 2 was we developed an expression for the rate of change for any amount of time from 1 to 1 plus anything. So when you looked at this right here, when we said from 1 to 1 plus 0.5, then that meant that our h value was 0.5. When we went from 1 to 1.1, so again, think of this as going from 1 to 1 plus 0.1, that made 0.1 the h value. And so once we developed this expression from 1 to 1 plus anything, we were able to just sub in an h value in order to get these same responses. And so all that we showed in the last video, and that's why we developed this expression that you see right here. This process would be tedious to do over and over and over again, but once you develop the expression that you see here, we can now just sub in values for h in order to get these answers. And so that's going to make the process go by a little quicker. But anyway, once we have this expression from 1 to 1 plus anything, we can continue to zoom in or approach 1. So it's the idea that h is getting smaller and smaller and smaller over time. So again, notice in the very first example that we did in lesson 2, right, from 1 to, think of this as 1 plus 1, so h was 1, then h became 0.5, then h became 0.1. h is getting smaller and smaller and smaller, and so what we're looking for is as h gets smaller and smaller, or in other words, as h approaches 0, what are the results that we're getting? So if we look at the results that we're getting as h gets smaller and smaller and smaller, what is the value that we are approaching here to get our instant rate of change? So this is now how we can kind of finish off this process. Let me give you the first obvious part of this first. So starting with this idea, we have this expression of 0.5 minus 0.25h. Right, that's the expression that goes from 1 to 1 plus anything. So what we're trying to figure out here is, remember, h is getting smaller and smaller and smaller because we're trying to zoom in on this value of 1. So the way that you're going to see this written, here's kind of the notation, is we're going to say the limit as h approaches 0 of this expression. Well, let's think about this logically for just a minute. If h is approaching 0, what am I going to be left with? So as this term zeroes out and goes away, you can see we're going to be left with 0.5 or 1/2. So I can kind of state the obvious answer right off the bat. As h approaches 0, I'm left with a value of 0.5. So we already know that our answer is 0.5. There's some work we have to show for that, but we already know the solution. So again, here's the idea. We now know the instant rate of change when t equals 1 is 0.5. So that's what we just accomplished with that process. So as we develop this expression with this idea, so we made h smaller and smaller and smaller so that we were getting closer and closer and closer to 1, right? So as h approached 0, then our result of 0.5, it becomes the instant rate of change that we are approaching as h approaches 0. Here's what you're going to be asked to show for that, though, is we have these h values that we are plugging in to the expression 0.5 minus 0.25h. All right, that was kind of the function that we were subbing into. And so we started off with allowing h to be 0.5. And when we sub that in for h, the result was 0.375. And then h became 0.1. And when we subbed in the 0.1, we got 0.475. Well, in this table, what we're going to show is clearly we're going to be approaching 0.5 as h gets smaller and smaller and smaller. And here's how you show that. We have to go 2 more lines, and we're going to show h as 0.01 and 0.001. So we have to go, that's as far as we're going to go, but we have to sub in those 2 numbers in for h. So just to go through that a little quicker, what I do is I just create the function right here for h, and I'm going to graph it, and I don't even care about the graph. What I'm looking at is the calc feature for value. So if I go under calc and choose value, then I can now sub in 0.01 in for h. And here's the result that I get. So 0.4975 is the result at 0.01 for h. And I'm going to go one more time, go under calc, choose value, and use 0.001, so 0.49975. Anyway, if you kept on going, you can see what value we are approaching. So as h gets smaller, as h approaches 0, the rate of change approaches 0.5, right? We're getting closer and closer and closer to 0.5 as h gets smaller. So even though we can logically look at this and say, well, as h approaches 0, I can tell I'm going to be left with 0.5, but we need to show that within this table. You're going to be asked for that. So this is a table that you need to show. And you don't have to show the 0.5. What you need to show are the bottom 3. So you're always going to set up your table this way with h and the expression for h. And these are the 3 numbers that you will always use for h to show what we are approaching as h approaches 0. So when you're asked to show a table to represent this solution, this is exactly what you're going to show. So lay it out the exact same way. And again, you don't have to use the 0.5. I just wanted to start there because we did it up here. But those are the 3 numbers that you're always going to plug in for h. And then these should show the value that we're approaching right here as h approaches 0. But that's it. That's our limiting process. It is a little bit of a tedious process in order to get this instant rate of change. We're going to get some shortcuts to that in chapter 24, but this is the heart of where all that is coming from. So to be continued on this for chapter 24, we'll get those shortcuts, but this is just simply what we need to know for now for chapter 23. And then one more thing I wanted to mention, as you're doing this idea right here, keep in mind that we were using 1 and 1 plus h because ultimately the goal was for us to get a instant rate of change when t was 1. So because this is what we were looking for, we used 1 and 1 plus h. If we wanted to know the instant rate of change at t equals 2, then we would have used 2 and 2 plus h to get a different expression. If we wanted to know t equals 3, then we would use 3 and 3 plus h within this process to get a different expression for t equals 3. So keep that in mind. This can change depending on what your ultimate goal is right here.